Good afternoon, everyone, and thank you very much for joining us for now the 8th webinar in our Offshore Wind series, Learning from the Experts. I'm Adrienne Downey. I'm the Principal Engineer for Offshore Wind with the New York State Energy Research and Development Authority, NYSERDA, and it is my great pleasure today to be joined by two of the industry's leading experts on the topic of resiliency. We're going to welcome Neil Weisenfeld and Garrett Moran of ICF. Who'll be giving a presentation on offshore wind resiliency planning. But before I introduce our speakers, just a few reminders, please, for participants and some background on the webinar series. So next slide, please. Very good, thank you. So first of all, if you are experiencing any technical issues at all, please contact Sal Graven per the email address at the bottom of this slide. This webinar is being recorded as we speak, and the recordings and presentation of the slides for all webinars within the Learning from the Experts series will be available on NYSERDA's website at the address that is indicated here on the slide. All participants for the moment have been muted. We will try to reserve time for Q&A at the end of today's presentation. So please do use the Q&A function to submit your questions for the speaker, and we'll look forward to getting to those. Next slide, please. Good. So to help introduce this series, New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and of 100% zero emissions electricity sector by 2040. And so while offshore wind has been providing clean energy to other parts of the world for several decades now, this industry is brand new to New Yorkers. So with that in mind, we are providing to interested stakeholders and members of the public information that is accessible and impartial and opportunities for engagement on specific topics of interest. So as such, NYSERDA is hosting this educational webinar series, Learning for the Experts, in order to connect the public with those independent experts in key topics relating to offshore wind. We endeavor to select Learning from the Experts speakers based upon their expertise, not necessarily for alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, please, by all means, email us at offshorewind@nyserda.ny.gov. Furthermore, we'll just conclude by noting that the views and opinions expressed in this presentation are indeed those of the presenter. Next slide, please. Wonderful. And so it is without further ado my great pleasure to introduce Neil Weisenfeld and Garrett Moran. Neil is a senior energy resiliency expert at ICF, where he assesses vulnerabilities and manages risks to energy infrastructure presented by a fast-changing climate and extreme weather conditions, both in the US and abroad. He translates climate science into practical information for decision makers, conducts risk assessments for assets and operations, analyzes costs and benefits of resilience actions, and supports long-term planning for climate adaptation and resilience. With over 35 years in the industry, Neil previously worked as the Director of Strategic Planning for Con Edison of New York. As well, we have Garrett, is a wind generation senior manager at ICF, specializing in wind turbine technology, turbine design, loads, and controls. Garrett has over 17 years of industry experience with a career in loads and dynamics and structural dynamics spanning the wind, aerospace, and oil and gas industries. He has worked for multiple international wind OEMs and on the space shuttle contract for Boeing for NASA and with deep sea offshore oil and gas risers. Garrett has further provided technical due diligence and financing support for nearly 5 gigawatts of globally installed wind energy capacity. So with that, welcome Neil and welcome Garrett. I will hand things over to you both, but again, thank you so much for being here today and for sharing your thoughts, opinions, and subject matter expertise with regards to the important topic of offshore wind adaptation and resiliency. Welcome to you both and thank you.
Thanks so much, Adrienne, and hello, everyone. Excited to be here with you today for this discussion of offshore wind resiliency planning. The agenda is listed here Adrian kind of gave the overview of who we are. We'll talk about how offshore wind is positioned to support meeting climate goals. We'll level set about the basics of offshore wind and how it works. Look at how climate factors play into offshore wind performance and reliability. See how those climate factors are projected to change by mid-century, and finally outline the adaptation options to make offshore wind more resilient to climate change. So Adrian did a great job introducing us. I didn't know Garrett worked on the space shuttle program. I'm going to have to talk to him about not telling me about that. So a little bit about ICF. Our company ICF is a global advisory and digital services provider based in Washington, D.C. or the D.C. area with over 7,000 employees and working in the areas of energy, the environment, transportation, digital technology, and health. So an important context here is the New York State Climate Leadership and Community Protection Act. So this CLCPA advances a set of ambitious goals to help mitigate climate change out to the year 2050. And those goals include decarbonizing the energy production systems by integrating renewables, and that includes offshore wind. And Adrian mentioned the goal of 9,000 megawatts of offshore wind by the year 2035. And so you see kind of the path to 2050 and the various moving parts that get you to the decarbonization goals. So offshore wind has a number of benefits. Certainly it's carbon free, and that is important in its ability to help mitigate climate change. It's got a higher energy output than onshore wind because the winds are stronger offshore, and the decarbonization component here can improve air quality, and particularly in dense urban areas like New York City, for instance, where the peaking units that will be operating at peak hours like today during a very hot day are particularly polluting. It is easier to site and less disruptive than onshore wind, although technically somewhat more challenging to operate and to install in the ocean. And it generates economic growth and benefit because of the jobs and the associated impact on the economy. When we think about the New York State CLCPA and its goals, it's just notable to see that the Northeast is actually a pretty good area for offshore wind. This wind map shows the potential across the US, with the red being higher wind speeds. And we can see that the wind potential is greatest from the New Jersey coast to the Gulf of Maine. So winds are somewhat higher at these higher latitudes, and hence a greater opportunity for offshore wind. And I'll just turn it over to Garrett to take us through the next couple of slides. Thanks.
Thanks, Neil, and hello everyone, and happy Wednesday. So let's define the offshore wind system. Of course, it consists of the offshore wind turbines themselves, any subsea cabling and electrical cables, onshore and offshore stations, transformer stations, met masts, and then onshore stations, as well as the port infrastructure itself required to construct the offshore wind facility. Next page, Neil. Thanks. So I believe this has been covered a few times in previous webinars, so I will very briefly touch on this. But how does a wind turbine work? Essentially, air flows over the blades, which have a lifting body shape, also known as an airfoil. This air movement creates a suction side on the top of the blade, which is turned into rotational movement of the rotor itself. This rotation in geared systems is up converted to a higher speed rotation into a generator to create electricity. But for most turbines offshore, they use direct drive generators, which are capable of generating electricity at a much lower rotational speeds. Next slide, please. So as a slight preview to our conclusion slide, these are the climate stressors, which we're going to cover in the following slides for the rest of this presentation. You can see the main climate stressors: wind, air, ocean, precipitation, extreme storms along the vertical axis and then horizontally, with the main components of the offshore wind system itself. You can see primarily the wind turbine generators are most affected by the environment and climate change, which makes sense when you think about that the turbines themselves are what are being touched by the environment and the weather and converting that energy into electricity. Predominantly the extreme storms, and with that extreme winds and storm surge, have the most impact on the turbine generators and then the onshore stations and ports. And then flowing into that on the next slide, please. Extreme weather is accounted for in the current international design standards in the IEC 61400-1 wind classes. You can see the VREF, T. T stands for tropical cyclones or typhoons, but that also means hurricanes. So they account in this design standard for an extreme wind speed, extreme reference wind speed of 57 meters per second. That's approximately 125 miles an hour, or about a Cat 3 hurricane in the design standards. Next slide, please. The international design standards for offshore turbine do account for wind loading combined with wave and current. This is in the IEC 61400-3, and what I have here on the screen is the main power production DLCs are 1.x for offshore wind that combines wind with wave. You see in the third and fourth columns there. Next slide, please. Back to you, Neil.
Okay. Thanks so much, Garrett. So I'm going to go through the factors here that affect offshore wind performance. And by performance, we mean the ability for the offshore wind system to meet several objectives over its operating life, such as project economics, including like the amount of energy generated, operations and maintenance costs, and climate change mitigation, such as like the avoided tons of carbon. There are certainly many metrics that are used for offshore wind, but we're making a distinction between performance and reliability, as you'll see on the next slide. So of the factors on this slide, it's not surprising that wind has the greatest relative impact, as indicated by these Harvey balls on the right there. Wind speed has the greatest impact because I think Garrett teed up the fact that the turbine output is linked to the cube of the wind speed. So a small change in speed can have a big change in output. Consistent wind direction is more desirable, as shifting winds can marginally reduce the output and can also increase the wear and tear on the components. The turbines have the ability to shift and follow the wind as its direction changes, but greater consistency is more preferred. Turbulence, intensity, and wind shear convey how smooth the wind is and how wind varies with height. So wind does vary with height. Near the ground, it is lesser in speed, and it increases with height away from the ground. Rougher surfaces perturb the wind and increase this shear, or this variation of speed with height. The ocean is typically smoother than the land, so there's generally less shear, but increases in waves, if in fact that does occur through climate change, has the potential to increase shear and affect output. Air temperature and moisture have smaller impact on offshore wind. A 5-degree Fahrenheit increase in temperature can reduce the output by 1 to 2% because warmer air is less dense, and so it has less energy. The moisture can impact turbine blades over time, increasing maintenance costs by actually slightly damaging the blades. For reliability, we mean the extent to which the system supplies output and avoids periods of temporary disruption as a result of climatic conditions, or certainly anything else that would occur outside of its normal operating range. So where reliability, or where performance is more about achieving the objectives over the life of the offshore wind system, reliability is about the kind of consistency of performance and the likelihood of conditions requiring you to shut down production temporarily. So not surprisingly, extreme storms have the greatest impact. And although these are accounted for in design, they can and have damaged wind turbines, as well as kind of the undersea and land-based infrastructure such as substations and ports. Winds above operating limit, even without storms, may require the turbine to shut down to avoid damage and can disrupt output. Ocean waves can impact the turbine support structures as well as the undersea components like cables and moorings. And frozen precipitation can impact turbine blades and cause potential damage. Sea level rise is shown as having a smaller relative impact. It is accounted for in planning and design, but does have the potential to corrode components and affect the vertical wind shear. So that wind profile that could cause increased wear over the life of the assets. Also, coastal infrastructure such as substations and so on can be impacted by sea level rise if not protected and if adaptations are not deployed. So what does climate science project for these climate factors in this area by mid-century? So the answer is it kind of depends on what you're talking about. The projections for wind in the Northeast are uncertain. Global speeds declined actually in the mid-70s, but they began to increase again beginning in 2010. So it really is uncertain as to where they'll go, and kind of the current thinking is that there may be decadal variations in speed. And so really what that says is, climate science, I think, as we're aware, is an evolving area, and monitoring the latest science is important. Temperatures are projected to increase. Talked about the 1 to 2% impact of a 5-degree increase in temperature. So a little bit of reduction in turbine output. However, there is an interaction between temperature and sea breezes that may act as a counterbalance to those reductions by invigorating the sea breeze. Hurricanes are interesting. So as the planet warms and water warms, warmer water has more energy, and so that will support higher or greater intensity of storms. So the number of storms in the North Atlantic is projected to remain the same or even slightly decrease, but the strength of those storms will be greater, and so you'll have a higher frequency of stronger storms that will potentially make landfall. The other factor going on here is that the projections show that storm tracks may move somewhat further offshore, and that may allow storms to have a greater likelihood of impacting offshore wind. Nor'easters have projections showing some really substantial increases, but both in frequency and intensity, and that's also the case for precipitation. There may, however, be less frozen precipitation because of global temperature increases, but the higher storm strengths may result in just an overall increase in icing, which may have the potential to damage blades. Sea level is projected to increase up to 30 inches by mid-century. And the fact that hurricanes may track further offshore may moderate one of the impacts of sea level rise, which is the potential to increase the storm surge. So higher sea levels combined with the surge that heavy storms can produce can drive that storm surge further inland. And if hurricane tracks shift further offshore, there may be a moderation of that. So all told, there are a lot of uncertainties in how climate change will impact these particular factors. So offshore wind has the potential to impact um, communities and wildlife, and that is considered in planning and design for offshore wind. Overall, wind power has a significantly lower impact on avian species compared to fossil power. And here, the number here is 3%, and the attribution for these numbers are in the report, which you'll find on NYSERDA's website. So there are about 130 references there, and they're all there. The question here we were dealing with was, what's the potential that climate change will change the dynamics between wildlife, communities, and offshore wind? Will climate change drive wildlife to interact with offshore wind to a greater degree, and therefore change the dynamics and the potential impact? And really the answer was no indication based on the literature review, kind of the latest thinking in science, that avian species will move further offshore because of climate change, or that increasing temperatures of the oceans will change the dynamics of sound propagation so that underwater species will be more impacted. So no clear indication there. And as far as turbine sound, the locations of the tracks that have been identified for offshore wind are more than 14 miles offshore. They're just too far to be perceptible. And so then the question was, well, what's the likelihood climate change, either air temperature or air moisture, will change that dynamic? And we did look at that, and there just isn't enough of an impact out to the mid-century at all to conclude that someone on shore will be able to hear the turbines or even see them. So I think, Garrett, you're going to take over and tell us, what do you do to the turbines and structures in the face of all of this? Thanks.
So what are some things that we can do, or designers or operators or OEMs can do for turbine resiliency to changing wind speed, direction, and shear? So as Neil mentioned earlier in the presentation, wind speeds have a direct impact on turbine performance, and there are some passive and active technologies that can be incorporated both in the field as well as part of the initial design and at manufacturing to help mitigate the impact of increasing or changing wind speeds. Vortex generators, gurney flaps, stall strips, and aeroelastically tailored blades are all passive technologies. Some can be done in the field, some must be done at design and manufacture. Microtabs, flaps, active flaps, and Lidar are active technologies. And in the following slides, we'll get into more details on some of these items themselves. For changing wind speeds, you could also have just more robust designs, right? Increased international design standards in prediction of periodicity of extreme weather as well as severity of the extreme weather. That VREF-T that I mentioned earlier, increasing that value. Typically, the international design standards look at the historic trends of weather and then project that into the future. That is no longer really valid when we take into account the impact of climate change going forward. Changing wind direction. You can have improved and more robust pitch and yaw systems to be able to respond more quickly or under increased load to changes in the wind. The blades themselves can be designed to operate in larger angles of attack. That allows the turbines to maintain peak performance as the wind direction frequency changes or increases. Change in direction frequency increases. And then of course, increased operation and operational and maintenance spending and planning and investment. For changing wind shear, you can look at taller towers to get up into the vertical shear, or Lidar with more robust pitch and yaw systems to respond to changes in horizontal shear. Next slide, please. So looking at VGs, they're essentially fins on the suction side of the blade that maintain the flow attachment along the blade core direction. They are often used and added in the field or at the time of install to boost the power and the performance of the turbine, but they do result in increased loads. Typically for offshore wind, I would expect these to be on the blade before the blades are installed on site over the water, but they can be a retrofit if needed. Next slide. Gurney flaps. So they are added to the trailing edge of the blade. Again, these are passive technologies. They increase the pressure on the suction side of the blade, improving performance and maintaining the boundary layer to the trailing edge. They do act as cord extenders, and they can also delay stall, but in doing that, they also increase loads and performance. Again, these would likely come on the blades before they're installed over the water. Next. All right, aeroelastic tailoring. So this is a passive technology that needs to be done at time of design and manufacture. This essentially couples the bending of the blade in either the flap or the edgewise direction with a torsional degree of freedom. So as the blade bends, it pitches out of the wind and passively reduces loads. There are two main methodologies to implement this into the turbine performance. One is through the physical sweep curvature. You can see on the center and right pictures, the blade itself is actually swept into the downwind direction of the blade. What this does is as the blade bends, it pitches out of the wind and reduces the loads and performance. So as the design is tuned, you can actually make a blade perform the way you want it to when it's flying dynamically. The other method to implement bend twist coupling is through material coupling of off-axis fiber directions in the blade shell or structural members itself. This is quite challenging because your manufacturing quality has to be top notch and consistent to be able to achieve the response that you want as the blade flies. Next slide, please. So some active technologies. You can use microtabs, synthetic jets, and stall strips. All of these act to control the flow in a dynamic and active way. Typically, synthetic jets and microtabs are kind of like dynamic VGs on blades. The challenge we have with any kind of active technology to address changes in wind or load control is that it has moving parts or some kind of electrical system that typically need maintenance. The more pieces that move, the more likely it's going to break. And maintenance and access offshore is significantly more expensive than onshore and more difficult. So this type of technology, while available, is oftentimes very much in the research phase or in the pre-planning, but is not flying in most modern day utility scale turbines. Microtabs and, sorry, if you go back for just a minute, Neil. Microtabs and synthetic jets, like I said, act like VGs to control the flow. Stall strips preemptively separate the flow before reaching extreme load conditions. Again, all of these can change the way the blade performs dynamically. Next slide, please. Lidar. So Lidar is a really cool technology, used quite a bit onshore presently. Essentially, Lidar looks upwind, and I use air quotes for that, so that the turbine can see what is coming down the stream tube and can proactively make corrective actions and dynamically respond to the incoming wind. So for instance, if Lidar sees a gust coming into the rotor can pitch out to catch that gust and not necessarily experience an overspeed. There are two types of Lidar typically used in industry. One is nacelle mounted upward or upstream looking, forward looking, and then there is ground mounted up, looking up. For offshore turbines, I would expect nacelle-mounted Lidar to be much more useful. I think putting a ground-mounted or surface-mounted looking up on a moving surface like the ocean or water surface would be difficult. Next slide, please. So active flaps, very much like an airplane wing. You can install active and dynamic flaps onto the trailing edge of a wind turbine to adjust and control the turbine, either reducing loads, increasing performance, individual pitch control, collective pitch control, and things like that. The challenge we have, again, with this very complex machinery is that there's a lot of moving parts. There's quite a bit of maintenance necessary, and typically flaps would be installed in the outer sections of the blade that are not accessible internally in the blade. And for those reasons, I would not expect active flaps to be used very often in offshore environments. I could see some type of movable flap that is sympathetic or responsive to external loads, but again, that would be more of a academic research project than current technology at the moment. Next slide, please. So turbine resiliency to sea level rise and wave loading. So we've looked at wind and changes in wind direction and speed and wind shear. What about the other main loading into offshore systems, which is wave and current? So wave loading is going to affect the foundation, whether floating or fixed structure, as well as the tower bottom of the offshore wind systems. You can have more robust foundation designs to withstand the increased wave loading. That includes heavier and more massive foundations, more massive or increased number of foundation bolts connecting the tower bottom to the foundation, as well as looking at the way that the cables and tethers come off of the surface, the water surface of the wind turbine and touch the sea floor. Make sure that there's significant length such that that touchdown point on the sea floor is not negatively impacted by the increased wave loading or increased motion due to the wave loading. Sea level rise itself is likely to have a minimal impact to offshore wind. Typically, the sea level is already accounted for in offshore designs before installation. However, if at some point in the future it does become more significant or critical, the designers and installers can always put the turbines at a higher elevation relative to the seafloor, maybe to account for variability in that sea level change itself. Next slide, please. So, extreme weather. I think, as I mentioned at the top, this is a significant impactor to offshore wind systems and wind turbines. One thing you can do is, as I mentioned before, account for the increased severity and frequency of extreme weather in those international design standards, not looking just at the past, at what has happened and projecting that forward, but actually accounting for changes in that future expectations. Heavier and stiffer blades to withstand increased loading, significantly due to extreme weather, increased severity of extreme weather. Of course, the turbines themselves will not be operating in something like a hurricane, but they're still going to be experiencing the extreme loading from that weather event. Stronger and more robust pitch and yaw systems. So the turbine, while idle during an extreme weather event like a hurricane, would still need to be able to track the predominant wind direction so that loading would be maintained within the intended design operational envelope, idle envelope, excuse me. So to be able to withstand higher loads and yaw the system, you need to have a more powerful and robust system. There are some more radical designs that have come about within industry in recent years. One is split pitch systems. You can see in the picture on the left, the pitch system is at about 1/3 chord of the blade span. That allows the pitch system to be smaller because it does not need to rotate the entire blade and still be operational in higher loads. The two-bladed system in the picture as well was designed by a Chinese OEM intended to operate in typhoons off the coast of Japan. The turbine, when a typhoon or extreme weather event is measured, goes into an idle mode, pointing one of the blade tips directly into the wind. So it's actually sitting facing 90 degrees off the predominant wind direction. By doing that, it allows the rotor itself to be dynamically stable and kind of weather vane with the wind and reduces loads by a significant portion, extreme loads. You can also look at downwind designs that allow the yaw systems to be undersized relative to upwind configurations, and the turbine itself essentially weather vanes with the prevailing wind direction to maintain the optimal orientation during the extreme weather event. Next slide, please. I realize we're running tight on time, so I'll try to go a little bit faster. Turbine resiliency to precipitation. So offshore tends to be wet, not unsurprisingly, and oftentimes very cold and icy. We can have hydrophobic blade coatings and paint to keep the blades clean and clear of ice if that's to develop. Other de-icing and anti-icing weatherization technologies in the nacelle, the hub, the rotor itself, whether it's forced air or heating through electrical lines or through pneumatics, you have ways of maintaining that temperature above freezing. And then, of course, real-time health monitoring and remote sensing to detect when there is an issue if the turbine starts to have a vibration because the rotor's imbalanced or what have you due to ice, and to take proactive measures at that time. Next slide, please. And back to you, Neil.
Thank you. Appreciate that, Garrett. So just want to cover building the resilience of coastal infrastructure. So I think, we keyed up the point that there is significant coastal infrastructure that is part of the offshore wind system, not just the substations that take the power and integrate it into the grid, but coastal ports that are used for staging and for the construction and maintenance operations. So sea level rise adaptations include either directly resisting sea level rise with things like seawalls, waterproofing, or nature-based solutions like wetlands and oyster reefs, or avoiding sea level rise by elevating infrastructure and hence allowing kind of the area below that infrastructure to be flooded, or retreating by potentially relocating a substation. Can't really relocate a port back from the ocean because you need water access, but you certainly can relocate substations. So for precipitation, increasingly heavy downpours can be managed by more robust drainage systems, porous paved surface technologies that can absorb water, and green infrastructure that can also be helpful. Increasing temperatures are going to affect everything that's in the ambient environment. And there's a direct impact and an indirect impact on infrastructure. So passive infrastructure like buildings and materials can be adapted by designing materials with the projected temperatures in mind. And we see that in kind of the New York City design guidelines for the city of New York, where they use climate projections and use corresponding knowledge of those projections to select materials. So the direct impact on components can be addressed by selecting materials. I think the other aspect is in just temperatures around an area can be helped by increasing tree and vegetation cover. So if you imagine a port and its integration with the community, you can use tree and vegetation to help reduce the extent to which kind of large paved surfaces might contribute to kind of the temperatures in the nearby community. As far as land-based infrastructure like substations, temperature impacts the capability of equipment and like transformers, and that can be addressed by having a projection and planning to a projection, and then planning the load forecast and load relief consistent with the ambient temperatures and the impact those ambient temperatures would have on capabilities of equipment. And we've seen that in, for instance, the Con Edison climate change vulnerability study that has a kind of a whole part that looked at those impacts, both from how load would be impacted and how equipment would be impacted by temperature. For high winds, existing structures can be reinforced consistent with those expected peak winds, And when planning, designing, and new infrastructure, wind peak gust forecasts over the life of the assets can be incorporated into the design of those new structures. So this is the table that we saw in the beginning, and I think just a couple of kind of takeaways we wanted to share here. First is that climate hazards like extreme wind and storm surge are currently considered in the design of offshore wind systems. However, climate change out to mid-century from our study has the potential to stretch design and operational limits. But given that designers and operators have a pretty broad range of options to build resilience of these systems. Some of these options, as both Garrett and I have covered, are available today and being used today, while other options are going to require continued development. And there's certainly a lot of thinking being done in this area. As far as the climate science, some of it is more certain than others, and the uncertainty really requires monitoring that emerging climate science as well as technologies to allow designers to incorporate appropriate resilience options into kind of future offshore wind systems. And with that, I'll turn it back to our organizers, and I think they will work through the Q&A. Thanks so much.
Thank you so much, Neil and Garrett. Really appreciate your input and presentation that you just shared. We do have a couple of questions that have come in, so we'll turn to those now in our remaining minutes here. Just before we do dive into Q&A, a couple of brief reminders again that this current webinar has been recorded. We will be posting it on NYSERDA's website for consumption here afterwards at your leisure. And also, if you have questions, please, by all means, feel free to submit them via the Q&A function of this presentation. We're eager to take your questions as best we can. So with that, turning to the first question, what can be done to mitigate risk in offshore wind development?
Sure. Neil, you want me to jump on that first?
Nope. Go ahead, Garrett.
So there's quite a bit that can be done, and in fact, in my group at ICF, we actually perform this for parts of these transactions. So every player, as part of the development for offshore wind and onshore wind, has their own self-interest to do a good job to mitigate risk, to protect their investment. So there's a lot of due diligence that is done at every step of the way, from very early greenfield developments and resource assessments to the financial transactions, construction monitoring, and operations and maintenance as you go through. My group at ICF, we do technical due diligence in support of the financial transactions for wind facilities. So we provide independent engineering, owner's engineering. Each developer, every bank, every financial institution, every government regulatory agency, everybody is invested in making sure that whatever proposed development is done well, is done right. It works well for the public, works well for the owner and the operator, and that everyone comes out ahead. And so at each step of the way, there is due diligence done, either technical or financial or regulatory, environmental, permitting, to make sure that everything is done properly. Neil, I don't know if you want to add anything to that.
No, nothing to add to that. Thanks so much, Garrett.
Great, thank you very much. A second question, how do turbine OEMs, so the manufacturers of wind turbine components, address the uncertainty related to future climate change, especially relating to changes in wind and extreme storms?
So I guess I'll take that one as well. A lot of this is done at the design, early design practices of these turbine OEMs. Oftentimes it is current onshore turbines are designed very tightly to the load limit because it costs money to be robust. For offshore wind, I think we need to take a bit of a different tact to where the turbine components, the blades, the nacelle systems, any moving machinery are more robust and are able to withstand larger ranges of loads within site. A perfect example of this is offshore's adoption of direct drive machines. Typically, most onshore machines are geared, and gearboxes themselves require quite a bit of maintenance and do have a tendency to break down before the end of the operational life of the wind turbine system. Direct drive machines, while more expensive and heavier, at times, depending on the magnets, do have less moving parts and are more fundamentally robust for the offshore conditions.
Great. Thanks again, Garrett. Appreciate that input. I'm wondering if we can turn a little bit, a question here. What are some of the challenges regarding the intermittence of wind energy, and how can we address them either by design or operations?
So I think wind as a resource is inherently intermittent. So you look at the wind distribution for a site when you're planning a wind site or a wind facility, and there is a distribution of wind both during the 24-hour day cycle as well as seasonal throughout the year, and that is calculated into the expected performance of the wind facility, both in energy generation as well as capacity factor and efficiency. All of those are part of the full assessment in deciding when and where and what type of machines and what brands to use, and the expected performance that you get out of it. There is some physical limitations in the amount of energy that you can extract from wind, just based on physics themselves. And then there are also inefficiencies within various kinds of turbine systems that you can work to improve, but at some point you are going to be able to extract only a certain amount of energy from the wind itself. Typically, you don't want to put a turbine where the wind doesn't blow. And that, I think, addresses some of the intermittency in the nature of wind. That's why onshore, the Tornado Alley through the center of the U.S. and those coastal regions in the slide that Neil presented earlier are so appealing, because the wind does generally blow there a lot and consistently. Offshore wind is more consistent and more smooth than onshore. You have a flat surface, essentially, that the wind is moving. It tends to be more dominated by directionality. So you can expect your offshore turbines in general to respond less frequently, or need to respond less frequently than onshore. So there are quite a few advantages for offshore wind in that respect.
Just want to jump on that. And,
Please.
the other thing that comes to mind is the CLCPA has, I think it was 3,000 megawatts of battery storage as a goal, energy storage as a goal by 2030. And so, I mean, moving to renewables, it's the intermittency of offshore wind, I think, as Garrett kind of laid out, is it's controllable only in where you select, and you do your due diligence and so on, but you will have to deal with a reasonable level of that. And battery storage is the other side of this, that will come into play in order to make this energy future practical.
Thanks, Neil. And thanks, Garrett. Wondering if we can pivot a little bit. There's a question here asking whether or not any of the technologies, in particular that Garrett shared, are more suitable for fixed bottom versus floating units, and if there's any differentiation there.
So I think in general, most of the technologies I shared are up tower. So they're mostly on the rotor or within the nacelle themselves. Floating foundations, maybe it's not a misnomer because they are not fixed to the ground, but they don't bob and move with the surface itself. Think more of offshore oil and gas foundations. They are, yes, floating in the water, but they are tethered and anchored to the sea floor and not moving around a lot. In that respect, in a lot of ways, from the foundation up, the turbine is the same, whether it is floating or whether it is fixed, a monopole or what have you. So all of the technologies on the blades, on the rotors or the nacelles, the nacelle mounted Lidar, all of that would work regardless of the type of foundation the turbine might be on. And as I'm saying that, the only thing I'm thinking is, depending on the amount of movement that you might have with the floating versus the fixed, there may be a small amount, and that would definitely affect the efficiency of the Lidar system if it was nacelle mounted looking upwind.
Then you would put on your NASA hat and put a gyro on there to keep it stable. Right?
You very could, right? You know, I can easily imagine a stabilization platform on top of the nacelle that the Lidar mounts onto. And in much the same way, you could do something like that for upward-looking Lidar, actually installed on the ocean surface or the sea surface, that allows some level of, you know, wave and current changes, and yet still gets a good view up. So, sure, it's
So
cool
Adrian's
tech.
an engineer.
Sure, get your
that-
pens out.
Yeah.
Adrian is an engineer as well. So this is what happens when you put three
Basically taking
engineers
notes.
together.
I love that
Start
stuff. Yeah,
solving.
absolutely.
No, I'm curious whether or not, there's a great question here. Do any of the current, the framing here is current implemented, but rather I guess it's anticipated or forthcoming offshore wind projects employ any of the technologies that we've spoken about here today, or anticipate incorporating them?
So I don't know. I would make an assumption that VGs are definitely on some of the blades because those are pretty standard onshore, offshore, climate change or not. But the rest of the technologies, I actually don't know. Neil, do you?
I do not know.
No, good question, though, and one that
That was
we
a good
should we will look forward to following up with. I think part of what's interesting as well is, and this is always difficult for our audience to sort of understand the time scale. You know, we're talking about these projects really in the very near future, right? But many of the aspects, you know, turbine technology, specific turbine, specific turbine specifications. Now here I go. They are being evolved, you know, sort of now, right? So it's entirely possible that many of these projects will confirm turbine types that embrace many of these technologies. And of course, that's been part of our RFP efforts with NYSERDA, is to try to encourage, you know, uptake of as many sophisticated technologies as we can. But anyways, I digress. Back to the questions. Wondering about another very good question. All of the future environmental conditions and risks that are impacting the supply chain and workforce training solutions. So what is the intersection there between resiliency, climate adaptation, and supply chain and workforce training?
I'll give a shot at that one. So resiliency, workforce training, and what was the other dimension?
Supply chain.
Supply chain, yeah. Well, for supply chain, and I think what initially comes to mind is the availability of a technology that can be deployed, things that are more on the horizon and less proven are less likely to be either available or adopted. I think because designers and engineers like Garrett and myself and Adrian were, you know, particularly in the energy industry, you know, like to see that things have been proven. So I think, you know, as technologies are deployed, the supply chains, you know, may, you know, have to see technologies deployed and successfully before they become more widely available. I think in workforce training related to resilience, you'd have to give that a little bit of a thought. I guess, I think if you come from the perspective that to solve the problem is going to require some level of innovation that maybe is not happening today, I think it leads me to think that training is going to have to be flexible and adapt to have folks that can, you know, do what's necessary to solve some of these thorny problems. I think offshore wind itself is a specialized activity, and, you know, there are tremendous job opportunities that it creates, but being specialized requires training folks. You know, I could imagine that the resiliency component of this and the thinking around that and what has to be done to meet objectives itself is going to kind of be somewhat of a specialization. Not clear how large that would become. Garrett, any thoughts on either of those, supply chain?
I actually do have some on the supply chain. I think this is a really good question, and this is kind of an aspect of climate change that we didn't necessarily address in our presentation. But there is a risk to the global supply chain to climate change. And you can look at it, well, this isn't climate change related, but the impact to COVID to global supply chains, the ship that was grounded in the Suez Canal that backed up quite a bit of international shipping. We being the world, are still recovering from the impact of COVID into global supplies. I mean, go try to buy a new car and you're going to pay above sticker price because there's just not much supply available. This happened in wind turbine components and solar components. We have design companies and OEMs that do the design in Europe or in the US or in China. Then a lot of manufacturing is done in China and maybe not where the design is done. Let's put it that way. Or you have an OEM who is contracting with a third party to actually manufacture the components. And those components need to be shipped to wherever the new wind site is going to be, in this case, New York. And so you may have shipping coming from South America or from China or from India coming to New York to be installed and commissioned. And that is I think that is exposed to risk due to changes in climate, due to changes in shipping lanes and availability of raw materials and availability of people to do the manufacturing and the installation. So I don't have a solution, but I think that's a really good point.
Great, thanks. Thanks both. I'm wondering, there's a question here, a good one, a nuanced one, about what is more concerning, reliability or performance?
So yeah, I want to hear Garrett's take on that. We've talked about that actually.
I would say reliability. So, I mean, yes, it's awesome to have a 15 megawatt machine out there spinning and producing just a ridiculous amount of energy. But that turbine needs to be reliable and consistent and to be producing energy as expected, as predicted, not only for the financial interests in the development, but for the consumers of the electricity. You need to be able to consistently perform and as expected and be reliable in the way that you perform and the way that you operate. No one wants to install a really shiny new machine out in the ocean and have it break 6 months later because the component, for whatever reason, I don't even know why. I would say reliability every time.
But and just to be clear, you're talking about the ability to meet the performance objectives over the life of the asset.
Right.
Yeah, because I think we called that performance in our slides, but okay. Life, yeah. rather than so not the short disruptions, but that ability to meet those objectives and be, not to use the word reliable, but not have maintenance issues and downtime such that over the life of the asset, you're not getting the energy production you wanted. Is that?
Yeah, and Neil, you brought up a good point too that we did not touch on, but is an interesting topic for offshore wind is useful life. So oftentimes turbines are designed for 20 or 25 years by the OEM. Most operators want them going for at least 30 or stretching to 35, and offshore wind is no exception in that. You don't want to have a machine that lasts 8 years offshore or 6 months or what have you. And because access and O&M and getting a person on site offshore is so much more expensive and challenging, you really want to have high confidence in your useful life expectations for your facility so that it will operate reliably and perform well.
Those are great clarifications from both of you, and I think it speaks to some of your earlier questions or your earlier responses about the alignment of the diligence, the financing community. It's really with that long-term view, right? 25 years as the minimum design standard, but that eager to support the viability and the longevity of the assets for as long of a frame as they can. No, it's interesting. But one last question, because we're really just coming up on time, but it's a good brass tacks kind of question to close this out. What about the relative costs of these technologies? And if we can close up there, hopefully we can point folks in the direction of our slides and close out.
So, relative cost of technologies, that's such a broad question, I think. If you implement it into the design process and at manufacturing, the cost is relatively minimal to add some technologies. If you're renting a boat or chartering a boat and going on site and pulling blades down to glue VGs onto them, that's going to be very expensive. Lidar is rather expensive, but has a direct and measurable impact to performance. Same for most of these technologies, actually. They do have measurable impacts, but most technologies, I would say, need to be incorporated at the time, at least at the time of manufacture, if not beforehand. Retrofits and in the field installs tend to be more costly just in general, and offshore even more so.
Great. That's great, Garrett. Really appreciate your answer. We are really at time, and so need to close out. Our thanks very much, Neil and Garrett, for your time today and for sharing this presentation. Thank you to our audience for joining us today for this latest installment of the Learning from the Experts webinar. A reminder that this webinar, its recording and presentation slides will all be available on our website, which is offshore-webinar-series.ny.gov, or more specifically, nyserda.ny.gov/offshore-wind or offshore osw-webinar-series, excuse me. As Neil and Garrett mentioned earlier, and for those who are eager to learn more on the subject of climate adaptation and resiliency, I would very much encourage you to spend some time with NYSERDA's offshore wind climate adaptation resiliency study that was published earlier this year, that can likewise be found on our website, and can be found specifically if you go to our resource library. The next webinar in our series is coming up quick, July 28th at 1 p.m., where we're going to be joined by Chris Oleth of the Special Initiative for Offshore Wind, who is going to be presenting on the subject of offshore wind stakeholder engagement, another really important topic as we seek to grow this industry and this resource opportunity for New Yorkers. So please join us then. In addition, we also have lined up August 11th, a review of the Construction and Operations Plan, or COP, review process with Michelle Morin and Jessica Stromberg of BOEM joining us. So please, as always, thank you so much for tuning in. Visit win.ny.gov to register for these future events. Thank you so much for joining us. Thank you again, ICF team. Really appreciate everyone's time and wish you all a wonderful, wonderful summer. Thanks all.
Thank you very much.
Thanks so much.
Bye
Thank
all.
you.